So all of you go to Google Collaboratory. New notebook. Now, if you go to edit and notebook settings, hardware accelerator, you have this GPU and TPU. GPU is graphical processing unit, TPU is tensor processing unit. In deep learning, we use tensors. That is a different data structure. I'll introduce to you, like how we use data frames, 2D matrix, 3D matrix. Like in that way, tensor is a format which is developed by Google for images, faster processing of images. So you have GPUs, graphical processing unit, and tensor processing unit. We will be using GPUs. And then click on save. Okay. Neural networks need graphical processing units. It doesn't work well on CPUs. So if you are looking at deep learning, advanced neural networks. Deep learning is nothing but advanced neural networks that has many hidden layers with each layer having hundreds of neurons for data processing. So deep learning is nothing but advanced neural networks. In normal MLP classifier or MLP regressor in Python, we can build up to 3 layers. But if you are going to build hundreds of layers with hundreds of neurons per layer, you need graphical processing unit and large scale computing. Deep learning requires graphical processing units or GPUs for faster processing of data. So free GPUs available at Google Collaboratory and Kaggle. 2 places where you will see is Kaggle and Google Collaboratory. In Google Collaboratory, you will get only Python. In Kaggle, you will also get R. You can use, if you want to use GPUs in R, you have to go to Kaggle. Kaggle provides GPUs for both Python and R, whereas Colab provides only for Python. So deep learning is predominantly used in image processing, like medical images, satellite images, maps, and also in natural language processing. In natural language processing, like chatbots, speech translation, etc. ChatGPT is the latest version. If you have seen ChatGPT, it is the latest version of full version of AI using neural networks. So if you're looking at machine learning versus deep learning, so basically this is the difference. In machine learning, we need to train manually the algorithm. Whereas in deep learning, it self-learns. So here we have to manually train the algorithm by giving X and Y and all the cleaning, data pre-processing and all. Whereas in deep learning, it does its own feature extraction, it does its own model building, and then gives the output. No human interface. So that is the difference between an ML algorithm and a DL algorithms. Deep learning algorithms have the ability to self-learn. Self-learn, self-adjust, and self-correct. Okay. So the libraries are import TensorFlow, import Keras. So TensorFlow is the library actively developed by Google guys. Google developers have developed this library called TensorFlow. For deep learning and image processing, we have these two predominant libraries. We have PyTorch, we have other libraries also, which are there, but the one which are easy to use with less coding, with less syntax is these two libraries, TensorFlow and Keras. And tensor is a data structure which is used in this library for faster processing of data. So this is the difference. This is a two-dimensional matrix, which we use in machine learning and data science. Predominantly, when we use Python and R, we use 2D data frames, right? But when you look at images, they are very high dimensional. So a tensor is a n-dimensional matrix. So it's very, very large. There are a lot of dimensions. This, for example, is a three-dimensional matrix. So tensors are the fundamental of TensorFlow, which is developed by Google for faster processing of large-scale image data. Okay. Now let us import our normal libraries. Okay. So from Keras dot data sets, import MNIST. X underscore train, comma, Y underscore train, X underscore test, comma, Y underscore test is equal to MNIST dot load data. So MNIST is a data which is provided by an institute in US of images, digits. We are importing it. The data is already formatted in X and Y, independent variables and dependent variable. Similarly, train and test data is already there. So X underscore train dot shape train X underscore test dot shape. So in train data, we have 60,000 images of 28 by 28, 28 height, 28 width. And in test data, we have 10,000 images of 28 by 28 size, 28 height, 28 width. So if you are looking at what are the images we are having, plt.im show, image show, X underscore train, square bracket 0, the first image. The first image is the digit 5. Handwritten digit images from 0 to 9. So MNIST is a research institute in US that has provided this data for developing algorithms to predict. So these are the handwritten images of digits. They have taken the digit, they ask people to write on a piece of paper the digits and they scan them and they store them in images as images 28 by 28 size. So the first image you can see in your train data is the digit 5. Digit 5. So they have also intentionally distorted the image to make the algorithms recognize effectively. Suppose if you want to see the first 25 images for I in range 0, 25 colon plt dot subplot open bracket 5, 5, I plus 1 plt dot im show X underscore train square bracket I plt dot xtext null plt dot ytext null plt dot grid false PLT dot show. So these are the digits from 0 to 9. PLT show outside the loop. Where is the PLT show? No, PLT has to be in straight line with fur. Got it? X-axis and Y-axis. We don't want X-axis and Y-axis. So that's why we are removing the X-axis and Y-axis. Or null. Null means we are not giving any values. Otherwise, in a graph, we get X and Y, right? Lines that we are making null. The first and foremost is the pre-processing. See, our data is in the form of images. These images need to be converted to the numbers. Images must be converted into numbers, pixels. Because we can't give images directly to the algorithm, it has to be only numbers. So pre-processing of images, first thing is reshape or convert images into pixels which is the numeric representation of data of image, and pixels range between 0 to 255. 0 to 255 is the range of the pixels. So x underscore train is equal to x underscore train dot reshape -1, comma 784. 784 is nothing but 28 by 28. 28 into 28 is 784. X underscore test is equal to x underscore test dot reshape -1. -1 is the shape of the dimension. 784 is 28 by 28. One shape dimension. -1 represents 1D. -1 represents 1D. One dimensional. One shape dimension. And 28 into 28 is 764. 784. So you can print x underscore train square bracket 0. Okay, now you can see the first image. Data is such large data. This whole zeros and all which you are seeing is the pixel data for one image. We have 60,000 such images in our data. In train data. This is for only one image. See amount of data which is generated for one image, which is if you look at the data, it is 0 to 255 maximum. Maximum is 255. 0 is the lowest. Okay, this is the pixel data for one image, first image of 5. The second pre-processing step is normalization or min-max scaling. Min-max scaling must be done to bring all values in range of 0 to 1 and only positive values. And only positive values. So min-max scalar must be applied on the data because we have 0 to 255 large numbers are there. Already neural networks are very complex algorithms. Computation is very, very high. So to reduce the size of the numbers, we have to scale the data. Min-max scalar will do it for you. Bring all the values between 0 to 1 and only positive values. Min-max scalar x minus x min divided by x max minus x min. This is the formula which is for min max scalar. So x underscore train is equal to x underscore train divided by 255 because min is 0. X underscore test is equal to x underscore test divided by 255. Min is 0. That's why I've removed it. Label encoding. Okay, now you can see, right? All the values are scaled to 0 to 1. Now, we will build a simple neural network model using TensorFlow. For building a neural network model in TensorFlow, we need certain functions. We need to import those functions and we need to use those functions for building the neural networks. The first function we need is sequential. Sequential, this is the model definition. Neural networks are sequential models. Neural networks are sequential models. One after the one layer it goes. Sequential is the model definition. Sequential modeling. One layer after the layer, the data will probably go in a sequential manner. The second is dense. Dense is a function used to define the hidden layer and number of neurons per layer and also the activation function to be used in hidden layer neuron. So activation functions like sigmoid, ReLU, TANH, etc. are used. So in a dense layer, dense is a function to define a hidden layer. Dense is a function to define a hidden layer. In a definition of a hidden layer, you need to define how many neurons should be there in that layer. What is the activation function to be there, to be used, whether it is TANH, sigmoid, or what function, you have to specify an activation function compulsorily. After dense, we also use dropout. To drop least significant or irrelevant features. Independent variables or weights, because there are a lot of connectors, weights will be there. We have to constantly reduce the weights. That means the number of arrows that go into the model that we have to reduce. The final layer activation function depend on the model being built. Classification and binary sigmoid. So if a dependent variable is binary dependent variable sigmoid, classification and multinomial. Multinomial means more than 2, softmax. If your dependent variable has exactly 2 levels, the final layer activation function will be sigmoid. If your dependent variable has more than 2, like in our case, we have 10 predictions, 0 to 9. So it becomes a multinomial. So we have to use softmax. For regression, we use linear, or also called as identity. You also need to define an optimizer. Remember the gradient descent algorithm, how the weight adjustments are done. The weight should reduce in it. So optimizer must be defined like Adam or SGD, stochastic gradient descent. We have to define a loss function. Loss function is the function that will be reduced. RMSE is in regression. In classification, we have log loss function. 1 minus y into that logistic regression log loss function will be there. So loss function has to be defined. Categorical cross entropy is what we use generally for large scale multinomial data. And we also need to define metrics. So for classification, you can define metrics as accuracy. And for regression, we can define it as RMSE or R square. Here accuracy or F1 score is also there. We can define F1 score also. So a metric also has to be defined. So these are the various parameters which you need to define manually. Whereas in Python MLP, regressor and MLP classifier, most of it is automatic. You just need to give the function names there. Whereas in case of here, we have to define the layers explicitly using the function names. Okay. Now let us import the functions. From keras dot models import sequential. From keras dot layers import dense. So model is equal to sequential null braces model dot add dense. The first hidden layer 1024 neurons. Activation is equal to ReLU, rectified linear unit, which is widely used in image processing. Input underscore shape is equal to 784, comma. So in the first layer, you have to give input shape. First layer, you also have to give input shape, 784, 28 into 28, 784. Model dot add dense 128 neurons. Activation is equal to value. Model dot add dense 10. This is the final layer. Activation is equal to soft max. Activation is equal to soft max. Model dot compile optimizer is equal to Adam. Adaptive momentum stochastic descent. Loss is equal to categorical underscore cross entropy, comma, metrics is equal to square bracket, double quote, accuracy. model dot summary. We are building a model with 9,36,330 weights. ReLU, rectified linear unit. We have discussed the activation functions, na? Max of 0, comma z. If the value is negative, it will be assigned 0. Whatever is the z value, it will take. Input into weight. Sigmoid, tan h, ReLU, these are all the activation functions we have discussed in neural networks, calculation. Rectified linear unit is the activation function which does not give you negative values. If anything is negative, it will assign 0. Got it? So this is the model we are building with 9,36,330 weights. This model has 9,36,000 in that new Excel example which I shown you. In Excel, we have done that, right? Calculation where we have only 9 weights, 3 output and 6 input weights. If you remember, we have done the calculation in Excel that 9 weights only there. It took a lot of iterations and calculations. So here we have 9,36,330 weights. It's a very large model. Now we have to label and encode the dependent variable. Y underscore train is equal to TensorFlow dot keras dot utils dot to underscore categorical y underscore train. And then we have to give the number of classes 10. Y underscore test is equal to TensorFlow dot keras dot utils dot to underscore categorical y underscore test comma 10. Number of classes in the dependent variable are 10. Okay. Now we will fit the model. Model dot fit x underscore train comma y underscore train comma epochs. Epochs means number of iterations. Epochs is equal to 10 comma batch underscore size. How many images in each batch? It will do batch wise processing. We have 60,000 images, right? It cannot process all of them. Or individually, it is not possible. It takes a lot of time. So 128 images per batch. It will take 128 images per batch and then it will push it to the algorithm. Comma, validation data. Validation data is equal to x underscore test comma y underscore test. So train data is x train, y train. Epochs is 10. Number of complete epochs means building a neural network, correcting it, or adjusting the weights. Okay, that it is one process, epoch. Batch size is 128. Validation data is x train, x test and y test. So the final train accuracy is 99.63, test accuracy is 98.21. See, if I'm running on CPU, it is taking 16 seconds. When I run it on GPU, it is taking less than 4 seconds. What are the shape? Shape. Input shape, first layer. Input underscore shape. When you're defining model, input underscore shape. No, small s. Actually, categorical function, this one, it's not correct, run properly. So re-imported the data and ran it again. Okay. So there is one more little bit larger data which we generally use. We call it as fashion MNIST. Train underscore X, comma, label underscore Y, sorry, train underscore Y, comma, test underscore X, comma, test underscore Y is equal to fashion you have to import the data set. From Keras dot data sets, import fashion underscore MNIST. Fashion underscore MNIST dot load underscore data. Okay. So PLT dot IM show train underscore X square bracket 0. So the first image is the image of ankle boot. Image of ankle boot. So T-shirt, trousers, like that we have different categories of fashion. So these are the categories we have in our data. Copy the same code and change that extra into train X. This is the only thing you have to change. Copy the data from top and change the data frame reference. All right. So same process. If you look at the data, 60,000 and 10,000 images are there. Train underscore X dot share print test underscore X dot shape. So same 28 by 28 images, 60,000 and 10,000. Train underscore X is equal to train underscore X dot reshape -1 comma 784 test underscore X is equal to test underscore X dot reshape -1 comma 784. Okay. Again, train underscore x is equal to train underscore x divided by 255. Test underscore x is equal to test underscore x divided by 255. Normalization. Reshaping and normalization. Got it? Model 2 is equal to sequential. Model 2 is equal to sequential. Model 2 dot add dense (1024), comma activation is equal to ReLU, comma input underscore shade is equal to 784, comma. Let us make it 512. Model 2 dot add hence 128, comma activation is equal to value. Three, 4, 5. Model 2 dot add hence 10, comma activation is equal to soft max. The final layer. Here we are building 6 layers. 6 layers. Earlier we built only 2 layers. Now here we are building 6 layers. Model 2 dot compile optimizer is equal to Adam, comma loss is equal to categorical underscore cross entropy, comma metrics is equal to accuracy. Model 2 dot summary. Five lakh 18,410 weights. 5,18,410 weights. We'll make this 102400. 9,85,086. Got it? Now we have to label and code train underscore y is equal to TensorFlow dot keras dot utils to underscore categorical train underscore y comma 10 test underscore y So we have to label and code the train and test and train dependent variable. Model 2 dot fit train underscore x comma train underscore y comma epochs is equal to 10 comma batch size is equal to 128 comma validation underscore data is equal to test underscore x comma test underscore y. It's running for you. Okay. Finally, we got an accuracy of 91.25 and 89.13 on test data. Same error. Huh? So I think you are running shift enter after this thing. Run from top one more time. Not top, re-import the data. Where you have done the fashion MNIST load data. Na? From that onwards, you run all the cells. It will correct. See, this categorical thing, if you run it multiple times, na, it will label and code multiple times. It should be run only once. Instead of pressing enter, you are pressing shift enter and then you are entering the second time and you are running it again. So that is creating multiple labels. To avoid that, just fashion element download, run all cells from there. You have to run that label and code only once. That is why if you run it multiple times, it will create multiple labels. See, here in the system, this has to be 10. Our final output layer is predictions. Now we are predicting only 10. That is the problem. All right. So we'll take a break and come back and then continue on the convolution neural network. Concept is a little bit big. Take a break and we'll come back and. So CNN are deep learning developed for image processing. This is an exclusive algorithm which was developed for image processing. CNNs work on large scale image data. So a typical convolution layer, convolution network will have additional layers before the neural network starts. Here, the neural network will start at the end. The neural network will start at the end. Before that, we have layers that work on the images. We call them as convolution layers. These convolution layers will clean the image. They reduce the noise or reduce the problems in the images. So the convolution layers will reduce the noise or problems in the images and also reduce the dimensionality of the images and finally bring them to a stage where the neural network can actually work on that data. Because when you're looking at large scale images will have a lot of problems. The one which we have done MNized digits and fashion, they are clean images. There are no problems in those images. Typically, when you look at images, there will be a lot of distortion will be there. When you have data with lot of distortion like blurriness, what you call multiple images in a single image, half-cut images, all those images when you have, these convolution layers will help you to work on those images and extract the information from the image. So convolution layers are those layers that work on images. Their job is to pre-process the image and clean the image for the neural network to run effectively. Okay. So these convolution layers are the important context of the important part of the CNNs or convolution neural networks. See here, the neural network is starting from here. The neural network is starting from here. See the arrows? They come from here. Now, all these layers, convolution plus ReLU, pooling, all these layers are working on the images to clean them and process them to a phase where the neural network can work properly and effectively. So in convolution neural network, the first layer is the convolution layer. The first layer will be the convolution layer. So this is another representation. See here, convolution 1, 5 by 5 kernel, valid padding. So it is working on the convolution layer. This is another convolution layer. Then finally, you will get the neural network starting and the predictions will come into picture. So a convolution network. Okay, so the first layer is the CNN or the convolution layer. See here. This is the actual data. This is the actual data, which is there zeros and ones. Now a kernel or a filter, the filter here is a 3 by 3 matrix, 101, 010 and 101. This is called as kernel filter. Okay, this kernel filter is running on the our image pixels data, and it is reducing the image from a larger image to a smaller image. A convolution layer is very important. The first layer will be always a convolution layer where it applies a filter. Here it is applying filter 101010, right? And it is moving one step sideways, and it is creating a new feature matrix which is smaller in size compared to the previous matrix. This is what 1, 2, 3, 4, 5. This is a 5 by 5 matrix, right? Which is converted into a 3 by 3 matrix. A 5 by 5 matrix or a 5 by 5 image is converted into a 3 by 3 image using a kernel filter, which is a 3 by 3 identity matrix. It is an identity matrix, diagonals 1, right? Unit matrix. Filter is unit matrix where diagonals are 1. Oh no, this is not unit matrix. Sorry, because we have other than diagonals 1 also there. 101, 010, 01. So each matrix it goes on. So the convolution layer, the first layer is the convolution layer, which reduces the image dimensionality by applying a kernel filter . thereby reducing blurriness, sharpness, size, etc. without losing any information. Without losing any information. This is the important part. Without losing any information or without losing any loss of pattern, it will reduce the image size. So the convolution layer is the first layer in the convolution neural network. This is the first layer in the convolution neural network. Okay. The second important thing you need to understand is padding. Padding means adding a layer of zeros. Padding is adding a layer of zeros surrounding the image for effective edge detection. So padding is a process of adding a layer of zeros surrounding the image. Padding is the process of adding layer of zeros surrounding the image. See here, a layer of zeros is added surrounding the image such that the edges are detected properly. Sometimes in medical diagnostics and all, edges are very important. X-rays and all, the edges of the X-rays are also very, very important. So to make sure that edges are detected properly, padding is applied. Padding is adding a layer of zeros on the outer end of the image for efficient edge detection. So padding is also a very critical process that is done in convolution neural networks such that the edges are detected properly without any information loss. So padding, a layer of zeros will be added. Okay. The next is the pooling layer. Pooling layer is a 2x2 filter applied on convolution layer for reducing the image dimension. Two types of pooling are used. One is the max pooling and second is average pooling. Max pooling and average pooling are used to reduce the size of the image or dimension of the image. Now you can see here. In max pooling, we'll take the maximum value of the quadrant. Here we have 4 quadrants. In max pooling, you will take the maximum value of each quadrant. In average pooling, you will take the average of each quadrant. In average pooling, we'll average it. 12 plus 20, 22, 30, 52 by 4 is 30. Whereas in max pooling, 20 is the maximum value in the quadrant 1 that is taken. 30 is the maximum value in quadrant 2 that is taken. So max pooling means the maximum value in each quadrant will be taken. In case of average pooling, all the values will be summed and divided by the number of values, count of values, that we call it as average pooling. So pooling is also done to reduce the image size. Right? We have to apply pooling to reduce the image size for effective working. So two types of pooling is there. Then flatten. Flatten is a layer that converts data from tensor or matrix into a single vector, single column vector, which will be the input for neural network, which will be the input for neural network. Flattening is a process of converting after all the convolution layers and pooling layers, you'll get a matrix or a tensor of data. That has to be converted into a single vector, column vector. That process we call it as flattening. So if you are looking at flattening, this is the flattening process. So after processing, we got this final data. After all the processing, we got this data like this. This needs to be converted into a flat vector, reshaping, that's all. This process, we call it as flattening. Conversion of a matrix into a single column vector. Just a conversion into a single column vector. Because the neural networks will take only the input as single vector. So this is the output of all the convolution layers and max pooling layers. Finally, you got the data like this, which needs to be converted into a simple reshaping process. It is simple reshaping process. Then finally, we will be using sequential, dense activations, final layer activation based on type of data, optimizer, loss, and metrics need to be compiled. For the final neural network, we need to do all these things which we are doing on a normal neural network. So there are different types of convolution neural networks. There are different types of CNNs which were developed over a period of time. So these are the different types of CNNs: VGGNet, ResNet, DenseNet, InceptionNet, ExceptionNet. So these are all the variants of CNN, which are very, very, very large computing algorithms. See here, VGGNet, it's a very large computing algorithm, which you can't run it on GPUs also. It needs a lot of computing. See ResNet. So there are different versions of KNN which are there, which is your inception module is there. This is your ResNet, VGG. So there are different versions which are there, but this is the base version which we are going to use. We are going to use a base version. So let us import our libraries. Import pandas as PD. Import numpy as NP. Import matplotlib dot pyplot as PLT. Then we have to import the deep learning libraries. Import TensorFlow. Import Keras. TensorFlow and Keras. Okay. So from Keras dot datasets, import fashion underscore MNIST. X underscore train, comma Y underscore train, test, comma Y underscore test. Okay. All of you got the data? Now we will reshape the data. X underscore train is equal to X underscore train dot reshape X underscore train dot shape square bracket 0, comma 28, comma 28, comma 1. x underscore test is equal to x underscore test dot reshape x underscore test dot shape square bracket 0 comma 28 comma 28 comma 1. Shape 0 is number of rows. 28, 28, 1 is one dimensional. 28 into 28, one dimensional. We are converting the data. So reshaping is slightly different for CNN. X underscore train is equal to X underscore train dot as type float 32. We are reducing it from float 64 to float 32. Sixty-four bit to 32 bit to reduce the computational intensity. And normalizing of data. Label encode. All right. Now we have done the deep data pre-processing. Now we will import the functions from keras dot models import sequential from keras dot layers import convolution 2D, CNOV 2D, max pool 2D, batch normalization from keras dot layers import dense dropout flatten activation. Okay, let us build a model. CNN is equal to sequential CNN dot add convolution 2D open bracket 32 comma kernel is 3 by 3 activation is equal to value input underscore shape is equal to 28 comma 1 padding is equal to same. Padding is equal to same. CNN dot add batch normalization. CNN dot add, we will do the same convolution layer, but we will remove the input shape. Input shape has to be given only in the first layer. The next layer onwards, you don't need to give the input shape. We'll add the third convolution layer with 24 filter, 3 by 3 kernel. Fourth convolution layer, 64 filter, 3 by 3 kernel. Then 32 filter, 3 by 3 kernel. CNN dot add max pool 2D. Pool underscore size 2 comma 2. CNN dot add flatten. Now we will build the neural network. CNN dot add dense 128 comma activation is equal to value CNN dot add tens 10 activation is equal to softmax. CNN dot compile optimizer Adam loss is equal to categorical underscore cross entropy matrix is equal to accuracy. CNN dot summary. So this model has 8,53,218 weights. Okay. Metric is accuracy on the primary. You want, you can give F1 score and all also, but accuracy is the primary metric. Okay. So 8,53,218 weights. CNN.fit X underscore train, comma Y underscore train, comma epochs is equal to 20. Batch underscore size 128. Validation data X underscore test, comma Y underscore test. Okay, we're running on GPU only, right? Oh, that's why it is running slow. See, 7 minutes something it is taking. Edit. No, mine is GPU only. GPU only. Time run all. Now it has picked up. See, otherwise it was showing 8 minutes, 7 minutes something no, initially. If you run it, it was running on CPU, so that's why it was showing 7 minutes per epoch. Runtime, because that's a different processing, no? Run all. So 99 on train, 91 on test. Underscore categorical underscore cross entropy. Small letter. Cross entropy is small letter. Next week you are going to actually today night only I want to go, but I have to watch, so I have to take it. I So the final accuracy is 99.41 on train data, on test data 91.89. On a simple neural network model which we built before break, we got train accuracy of 91, test accuracy of 89. The same fashion MNIST which we built using simple neural networks. 6-layer network we did, right? This is convolution layer. So convolution layers drastically, not drastically, they, if you tune them properly, they increase the accuracy of the models. Fran, for all of you. So we'll stop here and continue the next session.